Training data for the YouTube algorithm maybe looks like this. Millions of users, each with their own age, country, language, preference scores for 1,000 or maybe tens of thousands of categories, stored in the form of a data matrix. Each row is one field or property, and each column is one user. As a result, the data requires a very large storage space. Also, when we train our neural networks to predict user behavior, the matrix multiplications applied on the data will take ages to compute because of its high dimension. Is there a way in which we can preserve the crucial information of our training data while still being able to retain the mathematical structure of our data so that it can be applied to machine learning directly? Dimensionality reduction is the task of reducing the number of dimensions of our data, while still preserving the most essential information. The algorithm we will discuss today is known as principal component analysis. To see it in action, let's try to compress an image using PCA. Here we have a picture of an orangutan. The image is 3000 times 1688 pixels in size, with 3 color channels. We first flatten our image to 3000 times 5064. No information is lost in this flattening step. Also, image dimensions are written as width times height, but the size of matrices are written as height times width, and we need to keep this in mind. Now we have an image matrix of size 5064 times 3000. Then, suppose we decide to reduce our matrix from 5000 times 3000 down to 48 times 3000. In other words, we treat each column as a data vector, and we reduce the dimensions of each data entry from 5064 down to 48. Since our compressed image is a very thin slice, this is what part of it looks like. We can reconstruct our image by performing the inverse operation, and this will give us the final image of the orangutan. How does PCA work? In short terms, it tries to find the most important patterns of our picture, and describe each section of the image as a combination of those patterns. If you are familiar with linear algebra, then the description should remind you of eigenvectors and linear combinations. PCA is an algorithm that can find the most important patterns in our data. Today, we will tackle this problem from a linear algebra perspective. A critical assumption for the problem is that the number of dimensions actually needed for our data is much lower than the face value. We denote the number of fields for the data as n, and we have m data points. And we also assume that the number of dimensions needed is actually d, where d is a number much smaller than n. For example, we assume that our training data can be specified by 48 dimensions instead of 5000. How do we express this in linear algebra terms? Remember that data points are vectors living in a vector space. If a piece of data is specified by 5000 values, then it is a point in R5000. Our data matrix would be a lot of points inside R5000. However, since our data only requires 48 dimensions, there are 48 knobs that we can turn to describe our data point. At this stage, we assume that each of these knobs would correspond to a linear movement of our point. In linear algebra terms, it means that there is a set of 48 basis vectors, and our data point would be a linear combination of these basis vectors. All the possible points would be the span of the basis vectors, which is a hyperplane in a high-dimensional space. Therefore, we know that our points must lie on a 48-dimensional subspace inside R5000. The next problem we face is, how do we find the subspace and the set of basis vectors? Given our assumption that the data points lie on such a subspace, then there should be a way to perfectly fit the subspace through our set of points. To do so, we need to formulate an optimization problem. Suppose that we can choose from all the possible subspaces, and we want to find the best subspace which can minimize the distance between the subspace S and our set of points, encoded as a data matrix X. To define such a distance, we could use the definition of the distance between a point and a plane, which is the distance between the point and its projection on the plane. The distance between the hyperplane and our entire set would be the sum of all the distances individually. Now we want to find a formula for projecting the point x onto the hyperplane. We denote the projected point as x sub s. Since we want to perform a projection, it is best to work with vectors, and we will work with U, the set of orthonormal basis vectors of the subspace S. Consider the first basis vector, and we want to know how our point x extends in this direction. The formula for projection is C1 equals to x transpose U1 divided by the length of U1. And since our basis vector U1 is normalized, the first coordinate of x in the basis of the subspace must be the dot product itself. Since we have the dot product for every coordinate of our vector, let's write x prime equals to U transpose x, and U prime would be the coordinates of the projection in terms of the basis of S. As we want to compare the vectors in our original high-dimensional vector space, we need to convert the coordinates of the point in the subspace S, which is x prime, back to the coordinate system of Rn. The projected point in Rn would then be x sub s equal to U times x prime, which is a simple change of basis. Hence, the projected point x sub s is equal to U transpose x. We rewrite our optimization problem using this notation, where we are trying to minimize the function by varying an orthonormal matrix. Since we are projecting a point from n dimensions to d dimensions, the size of U should be d times n. At this point, we can also rewrite the problem as the optimization problem of the distance between two matrices, x and U transpose x. Just like vectors, we can do something known as a norm function, which is like a length measurement, and we will be minimizing the distance between the two matrices, which is the length of the matrix difference. Just like how the distance between two vectors is the magnitude of the difference of the two vectors. For reasons related to the proof, we will replace our original definition of distance and use something called the Frobenius norm. The Frobenius norm is very similar to our original definition. While we originally sum up the distance of each vector individually, the Frobenius norm first sums up the squared values of all the entries and then takes the square root. Suppose that A is our difference matrix, and the Frobenius distance is the square root of 8, but our original distance definition would give us 1 plus square root 5 plus square root 2. This leaves our final formulation. Solving the PCA problem would be equivalent to finding the orthonormal matrix of size d times n, which minimizes the Frobenius norm of the matrix x minus U transpose x. And the solution to our PCA problem is d eigenvectors of the matrix XX transpose corresponding to the d largest eigenvalues. I will cover the proof of this fact next. There is another way to motivate this fact, but it is more related to statistics theory instead of algebra, so I may cover it in another video. Remember to like and subscribe so you won't miss out on any future content. How do the d largest eigenvectors relate to the description of PCA I mentioned at the start of this video? We find a set of orthonormal vectors of important patterns, which is the matrix U, and we project our data into this subspace of patterns. Then we will have a matrix of coefficients of the patterns U transpose X, and we need to recover our data by the linear combination of the pattern with the coefficients. The eigenvectors of XX transpose are the important patterns that we are trying to find. We will approach our optimization problem assuming that we do not know the solution, but we still need to know a few facts related to linear algebra. The first is that the Frobenius norm of a matrix is equal to the square root of the trace of A times A transpose. This fact can be easily understood by thinking of the matrix multiplication of A with A transpose, which is equal to the dot product of each row factor of A with itself. And since we are taking the sum of the diagonal entries and then applying our square root, this would be equivalent to the Frobenius norm. Another thing to note is that for the trace function, trace of A plus B is equal to the trace of A plus the trace of B, and the trace of A times B is equal to the trace of A times the trace of B. We will also use a very important lemma, which states that if A is a symmetric matrix and U is an orthonormal matrix, denote the eigenvectors and eigenvalues of A as v1 up to vn and lambda1 up to lambda n respectively. And we arrange the order 1 to n by writing lambda1 needs to be greater than or equals to lambda2 and all the way up to lambda n. And then the sum of the first d largest eigenvalues will be greater than or equal to the trace of U transpose AU. And to achieve equality, U will be the d eigenvectors corresponding to the d eigenvalues. A way to understand this relationship is that we observe that without the trace operation and the limitation on the size of U, we are dealing with the diagonalization of the symmetric matrix A, where we can write A equals to U du transpose, where U is an orthonormal matrix and D is the diagonal matrix of the eigenvalues of A. Using our intuition on diagonalization, we are trying to decompose the linear transformation A of x into 3 steps. First, we perform a change of basis of the vector x to decompose it in terms of eigenvectors of A. Next, we scale each coordinate of A proportional to the eigenvalues of A. At last, we recover our vector x in our original space by performing the inverse change of basis. When we are dealing with a limited number of dimensions, the amount of information that we can recover from our vector x should be maximized when it is decomposed into the corresponding d largest eigenvectors and eigenvalues of A, and other changes of bases would mean that we will not be able to fully recover our vector x, hence the intuition for the inequality. With the lemma in mind, we rewrite our objective function as trace of x minus UU transpose x times x minus UU transpose x transpose. We then expand and simplify our expression to get this. Using the first property of trace, we can break the expression into 4 parts. We collect the terms in the middle as the trace of a matrix is equal to the trace of its transpose. Using the second property of trace, we can move the U transpose matrix to the front. And then, as U transpose U is equal to the identity, we get that our final expression is trace of XX transpose minus trace of U transpose XX transpose U. Since the first term is constant, minimizing the expression would be equivalent to maximizing the term trace of U transpose X times X transpose U. And then, by using our very important lemma, we get that the solution to the PCA problem would be the first d eigenvectors of the matrix XX transpose corresponding to the d largest eigenvalues.